Hi, welcome to our VB Developing channel. Hope everyone is well. Today we are here with a new video. Today we will discuss, from Chapter 2, From Among Operators, about bitwise operators. So let's get started. But before starting, this part of this chapter is complicated. We tried to make it as simple as possible, so you won't understand anything if you skip it. Please don't skip it, we say. We have taken a lot of time to explain in the video. I hope you will understand if you watch the video patiently. Let's begin. In Python, bitwise operators are used to perform bitwise calculations on integers. The integers are first converted into binary, and then operations are performed on each bit, or corresponding pair of bits, hence the name bitwise operators. The result is then returned in decimal format. Note here, Python bitwise operators work only on integers. Notice here, this ampersand symbol represents the AND operator. And the result is, sets each bit to 1, if both bits are 1. And next, bitwise, or operator, sets each bit to 1, if one of two bits is 1. Next, bitwise XOR operator, sets each bit to 1 if only one of two bits is 1. Next, bitwise NOT operator, inverts individual bits. Next, bitwise left shift operator, shift left by pushing zeros in from the right, and let the leftmost bits fall off. And the last one is, bitwise right shift, shift right by pushing copies of the leftmost bit in from the left, and let the rightmost bits fall off. Now we will see the whole matter practically. Here we will first create a file, as before. First of all, here we will declare two variables. Now we using bitwise AND operator. Does anyone know how bitwise A and B are equal? Bitwise A and B are equal to 1. Let's check it. As you can see here, we got 1. Now we will try to know why we got 1. But one more thing is, to know this here, we need to know about binary first. Then we can understand it. Because it's about binary. So, let's understand what is binary. The binary number system is a base 2 number system, in which numbers are only represented by two digits, 0 and 1. A bit is an abbreviated form of binary digit, which is the smallest unit of data in a computer. A bit has only one binary value, either 1 or 0. It's important to note that the most significant bit, MSB, is the bit on the far left end of a binary number, while the least significant bit, LSB, is the bit on the far right end, LSB. 11102, 10012, etc. are examples of binary numbers. The binary system is applied internally, by almost all latest computers and computer-based devices, because of its direct implementation in electronic circuits, using logic gates. Every digit is referred to as a bit. Now we will convert the decimal number 5 to binary. Let's say one thing here: to convert to binary, you have to divide by 2, and that is until 0 comes. See here, first we divided 5 by 2, and got 1 as a reminder. Second time again we 2 divided by 2, and got 0 as a reminder. And third time again we 2 divided by 1, and got 1 as a reminder. And this is least significant bit, LSB. And this is most significant bit, MSB. See here, we have included it in the table here, to make it a little easier to understand. Now we will write the remainder in reverse chronological order, from bottom to top. Hence, the decimal number 5 in binary is 101. To know if the binary number we got here is correct or not, we will check it once in Python. Let's check it. Here we using bin function to convert decimal to binary. As you can see here, we got 101, which was binary representation of 5. Now take note here too. Here we have 101 as the binary of 5. So our calculation is correct. Okay, let's try to understand why we got 1 here. Now you notice here, binary representation of 5 is 101, which we have shown earlier. See here, binary representation of 3 is 011, we show you this once again. As you can see here, we got 11 as binary of 3. One thing to remember, every binary number is preceded by 0. We will see this later in the bitwise not operator. So here we have 011 as the binary of 3. Now look here, and get truth table. I hope many people know about this table. We have taken this table from the Computer Basics chapter, from the Logic Gates chapter. And here we discuss it, when talking about binaries. However, here we have used it, so that it is easier for us, to understand. Look here, 0, 0, 0 as output, 0, 1, 0, and 1, 0, 0, 1, 1, 1 as output. Now, let's perform the bitwise AND operation on these binary numbers. Now look here, 101 is binary representation of 5, and 011 is binary representation of 3. Now we calculate, 10 equals 0, 01 equals 0, and 11 equals 1. So, when you combine these results, you get 001 in binary. When you convert 001 to decimal, it equals 1. Therefore, 5 and 3 evaluates to 1 in decimal. Let's check it, convert A and B to binary and see what we get. As you can see here, we got 1 as binary, which we got earlier in our calculations. Here's exactly what we got. And this binary number represents the decimal number 1. Now we delete all these things, and execute once again. Here we got 1y, now hope everyone understood. Now we will change the value of variable b. Here we get 0, we will try to understand this, using the same method as before. Here we know, binary representation of 5 is 101. And we will now extract the binary number of 2. Here we can see, we got 10 as binary of 2. Now we writing here this binary, and we will add a 0 before this binary. Now we will calculate it according to this truth table. 10 equal to 0, 01 equal to 0, and 10 equal to 0, so we got here 000 as binary value, which was represent decimal number of 0. For that we have got 0 as decimal here. Okay, now we will use 2 more different numbers here to understand more clearly. Okay, here we have binary calculation of 63 and 13 to get 1100. Its decimal value is 12. Now we execute and see. Here you can see, we got 12 as decimal, whose binary value is 1100. Okay, we will learn about bitwise OR operator. Here you see, we use bitwise OR operator to get 7 as decimal. Let's try to understand it, why we got 7. Note, we have used OR get truth table here. Notice here, 0 0 equal to 0, 0 1 equal to 1, 1 0 equal to 1, and 1 1 equal to 1. Here you can see, after calculation we got 111, which was decimal value of 7. Let's check it. As you can see here, we got 111 as binary of 7. Okay, now we will learn about bitwise XOR operator. Here you can see, using bitwise XOR operator we get 6 here as decimal. Let's extract the binary number of 6. Here we get 110, as the binary number of 6. Let us look at the details. Note here, we have used XOR get truth table here. Now look here, 1 0 equal to 1, 0 1 equal to 1, and 1 1 equal to 0. So here we got 110, whose decimal value is 6. So that's why, here we got 6 as output in decimal, whose binary value is 110. Okay, we learn about the bitwise NOT operator. As you can see here, we get -6 using the bitwise NOT operator. Now let's try to know why we got -6. The binary representation of the number 5 is 00000101. This representation has several leading zeros, because integers are typically represented using a fixed number of bits, for example, 32 or 64 bits, and the leading zeros do not change the value. Bitwise NOT operation. The bitwise NOT operation inverts each bit. So, applying bitwise NOT to 00000101 results in 1111, 1010. Every 0 becomes a 1, and every 1 becomes a 0. Interpretation as assigned integer. the interpretation of the result as a signed integer is crucial. In most computer systems, integers are represented using a method called 2's complement. In 2's complement, the leftmost bit is the sign bit, 0 for positive, 1 for negative. In the case of 1111, 1010, the leftmost bit is 1, indicating a negative number. The rest of the bits represent the magnitude. To find the magnitude, you can perform the 2's complement operation, which involves flipping the bits and adding 1. For 1111, 1010, flipping the bits results in 0000, 0101. One thing to remember here, when we are flipping the second time, our number is coming back to the previous position. Adding 1 to this gives 0000, 0110, which is 6 in magnitude. Now we go to next page. Note here, after the first flipping we get it as the original number. Flipping again to use the bitwise not operator a second time, this returns our number back to its actual original state. Now we adding 1. After applying bitwise not, you add 1 to the binary result. This is part of the process to represent negative numbers in 2's complement form. Note one thing here, 1 plus 1 equal to 10, and 1 plus 0 equal to 1, and 0 plus 1 equal to 1. The final result of 1111, 1010, bitwise not of 1111, 1010, followed by adding 1 is 0000, 0110 in binary. Since the leftmost bit is 1, the overall value is negative. Therefore, bitwise not 5 is interpreted as -6. As you can see here, that's why we got -6 here. Okay, now let's try to understand with another shortcut trick. Now, we will know how bitwise not goes to -6, we will see step by step through shortcut method. At first we will extract the binary of 5. Here you can see, we got 101 as binary of 5. Here you see, after performing the bitwise not operation we got exactly the same. Now we will add 1, and the result will be 110. As you can see here, we got exactly the same. Which I got here. Note here, this number represents the decimal number of 6. which, I have shown here before, the magnitude of which is 6. Here again we see the binary number of 6. Here you will understand that, after adding 1 to binary number 5, and binary number 6, the result is same. Well, now we will just add a minus sign, since our number is negative. Here you can see we got minus 6 as usual. Now notice here, first we get 101 as the binary number of 5, then we add 1 to it to get 110, which is the binary number of 6, and then we add a minus sign which represents the negative number. And finally we get minus 6, which is bitwise not equal to 5. Okay, now we will learn about bitwise left shift. Notice here, we get 10 using bitwise left shift, which is a decimal number. Let us try to understand how we got 10. Let's see here, binary representation of 5 is 101. Left shift operation. The left shift operation shifts the bits of a binary number to the left by a specified number of positions. In this case, it's 5 left shift 1, meaning we are shifting the bits of 5 one position to the left. Now look here. Here is the current position of our binary numbers. Then when we do a left shift of 1, our number is moving one step to the left position, and leaving a 0 at the same time. Here you can see, the operation involves moving each bit to the left by one position, and filling in the vacant position with a 0. Now final result is 1010, which is binary representation of decimal number 10. Now let's check it practically. Here you can see, we got 1010 as binary number of 10, which we have shown here. Now let's try to understand the whole thing step by step. See here, it will first show us the binary number of 5. Secondly, it will show the decimal number obtained after the left shift operation, which we have shown here. Third, it will show our current binary state. That will show it. So, let's execute it. See here, first we show the binary number of 5, then we show the actual output, and last we show the binary number of the actual output. Hope you have a good understanding about bitwise left shift. Let's now try to learn about bitwise right shift. As you can see here, we got 2, using bitwise right shift operator. Now let's try to find out why we got 2. The right shift operation shifts the bits of a binary number to the right by a specified number of positions. In this case, it's 5 right shift 1, meaning we are shifting the bits of 5 one position to the right. Now look here, the current position of our binary is 101. After the right shift operation, now the binary position is 10, because one bit has shifted to the right. The operation involves moving each bit to the right, by one position. The leftmost bit is typically filled with the sign bit, 4 signed integers, 0 for positive numbers, and 1 for negative numbers. The binary representation 101 is shifted one position to the right, resulting in 010. The leftmost bit is filled with a 0. So final result is 010, which equal to 10, and which is binary representation of 2. Let's try to understand the matter step by step. Let's execute it, and see what happens. Sorry, we forgot to use the bin function here, let's add it. Here you can see, first we extracted the binary number of 5. After that we extracted the original result by right shift operation. And finally we extracted the binary number of 2 again, which became 10, which represents the decimal number of 2. Here we convert 10 to decimal and get 2, which corresponds to our output. Friends, we hope you understand about bitwise operator. Let us know by comment. Thanks for watching the video. See you in the next video. Subscribe the channel, don't forget to like. Thank you.